Okay, I want to show you a little bit of something here that I came up with, and it involves precession of propellers on control line airplanes, and people say that there's significant impact, or at least some impact of precession whenever the airplane makes a corner. And so I've got a standard propeller on this airplane right now, and if I do this right now, like this, you can hear the grinding noise that's happening, plus I can feel some motion in pitch. And that comes from the precession of the propeller. And it's fairly significant. So, I've been working on a project, and that project is a variable pitch propeller. And one of the things that I decided to do, I was concerned about, is the propeller moments on the shaft of the propeller, or the motor shaft. Not so much that, but the on the spindles for the propeller. And those spindles, they undergo bending whenever the propeller does maneuvers and so forth. In flight testing, when we test the full-size airplanes, the gyroscopic moments that occur on the propeller end up being some of the greatest moments, loads on that propeller that the airplane will experience in service. And so for the for my project propeller, I had this idea that borrows from helicopters. And a helicopter's tail rotor sees virtually no propeller moments. And the reason that is because of the flapping hinges, or the way that the tail rotor is hinged on the airplane, or on the tail rotor. If you go look at a Bell Jet Ranger's tail rotor, you'll notice that the shaft that tail rotor sits on is actually it's real spindly, and you look at it and you go, oh my God, that won't handle. But you've got this near 5 foot. I need another washer here to be able to put this propeller on. It clamped up okay last night. Don't know exactly why it's not clamping up now. It may be that this little spacer shim that I built is sticking out a little bit. Let's turn this washer over, because that washer was upside down last night. And so the tail rotor on that helicopter, that's not going to work. Okay, so where was I? I was talking about the Bell Jet Ranger and its tail rotor. And so if you look at the shaft that runs that 40 some odd inch tail rotor on that helicopter, it's just a little spindly shaft. And now that helicopter has a spin rate of about it's about 90 degrees per second, which on a control line airplane that would equate to 4-second laps. And you notice that when I do this with this particular propeller right here, there's virtually no precession. There's a little bit, the majority of which is probably from the motor. But it's considerably different. It's way different than the other propeller. I can do this very violently, and the airplane does not jerk around. So, why does it do that? Well, so if you go look at a tail rotor on a helicopter, it has a particular feature. It has a hinge in the middle. So, number one, the reason why rotor systems have hinges is it's to remove the bending load of the blade from the helicopter. And I could have got a helicopter down and brought a rotor head down and a tail rotor. The RC tail rotors tend to be fixed. They don't worry too much about bending. And so I stumbled on this particular idea quite by accident, and I should have known. I should have known the precessional effects because of my tail rotor experience. But I was in the variable pitch propeller design mode, and if you look right here, these hinges. This propeller is actually for an F1C model, and this is a 7.4. 7.3.5, probably not sufficient to fly this particular model, because this is the propeller that came off as a 7.5, and I could go out, and this airplane will probably get airborne with this 7.3.5 inch propeller. And my camera's not quite adjusted right, but you look and you see these propeller blades are allowed to hinge. That means that the propeller blades cannot transfer any moment to the hub because this is free like this. It pivots. It's a pin joint. No bending can be transmitted through a pin joint. It's simple, right? So what that means is when this propeller is moving, right, any mass moment of inertia or any precession as a result of the mass cannot be transmitted through the propeller to the hub. And further, it does not get transmitted from the propeller hub through the shaft into the airplane. So for the most part, the effects of precessions are eliminated. Now that's not 100%, because you notice that there is a small space between the centerline axis and my hinge points. And because of that, we're going to get some torque that comes through this hinge as a result of the blades flapping in plane. So why does that work? Okay, so it's very well known these days. Igor Sikorsky learned it the hard way, but today we've got lots of very, very smart people that have been doing this for a very, very long time. So if we take a propeller, and the propeller is on a shaft, it's running on an axis like this. We tend to treat this just exactly like a gyroscope. The question is this propeller truly a gyro? The answer is yes and no. The reason why it is pretty much because the propeller is fixed to the shaft. And because it's fixed to the shaft, the propeller blades can transmit a moment. And so if we took a propeller fixed to a shaft, or a rotor system fixed to a shaft like this, and we spun it in a vacuum, when there's no vacuum around, and we tilt it like this, it would indeed pivot, and it would indeed precess, and we would see that the change in motion would precess 90 degrees, pretty much. However, if we were to put this propeller on a frictionless joint so that it could teeter on the end like this, and we put it in a vacuum and we spun it, and we took this shaft and we tilted it like this, the moment of inertia, the rotating moment of inertia of the propeller blade and the angular momentum of this propeller spinning in that vacuum would cause it to remain in the place that it stands. It moves. So I can move this shaft around like this. As long as that joint is frictionless, I move this shaft all around, and that propeller will continue to rotate in plane. Now, if we take that propeller out of the vacuum and we run that propeller in air, the same one with the hinge, like this, right? It's going to pretty much do the same thing. And it's going to run always in the same plane. If on the other hand, the propeller is running and we see some air moving into that disc, what will happen is one of the blades, let me turn this right side up, what will happen is one of the blades moving in the direction of the air we'll see an increased lift because of the velocity of the rotation of that blade. So the lift would change by the rotational angular velocity of the blade plus the influx of the air coming into this disc, increasing the lift on this blade. The corollary happens is that wind coming to the downward moving or the reverse moving propeller would tend to decrease the amount of lift on that blade. Therefore, what happens is a torque is generated across the propeller, and because it's moving at a rate, it will precess. And because this is rigid, that angle of precession is going to be pretty much 90 degrees. It doesn't necessarily have to be 90 degrees, but for a rigidly mounted blade, it's going to be very close to 90 degrees. There's a whole lot of things that go into what that phase angle is between where the disturbing force is and the resultant change in angular velocity occurs. So a propeller or a rotor system is yes, it's kind of a gyro, but no, it's not. And it's a gyro because it's an airfoil and it's moving in the air. Now, if I take this system right here, and this is a flapping hinge. This is a folding propeller, right? And this is what caused me to do this test. I wanted to go, okay, so I knew this answer beforehand, but for some reason I wanted to do a test because I was questioning my design plans of eliminating the bending loads on my propeller hub for my variable pitch propeller by putting a wet hinge. And the question was so how well will that propeller stay in plane? I already knew the answer, but I wasn't thinking clearly. And so I did this test, and I was shocked by this result when I picked the airplane up and I moved it, and the propeller stayed in plane. And, the nose of the airplane didn't dodge all over the place. I went, oh, it's not precessing. Oh, lots of conversations went on inside the head here. I'm Gemini, so there's at least 2 conversations going on pretty much all the time. And so that conversation ensued. But so what happens is that just like the tail rotor on the helicopter, the tail rotor is allowed to hinge, and they put what's called a delta 3 hinge in that rotor system. So there's a hinge that goes about 45 degrees to the blade axis, and so the tail rotor is allowed to pivot. And when it pivots, here's what happens, right? If you look at the propeller or the hinge, the delta 3 hinge, when it pivots, as it goes out of plane, it increases the angle of attack of the descending rotor blade, and it decreases the angle of attack of the ascending blade. And so what that does is that increases the lift on one side, decreases the lift on the other side, and that causes the rotor blade to run and fly in plane and to stay in plane. Even better, what it means is that there is no moment, no torque on the shaft. So when this propeller is running like that, or this tail rotor is running on the shaft, there's no moment transmitted to the shaft itself. So that shaft can be quite spindly. What that means to the helicopter is there's no bending that goes into the shaft, into the gearbox, and into the tail rotor. And so there's no loads that are generated whenever that helicopter, we take the helicopter and it's hovering really nice and pretty, right? And we do a pedal turn like this, right? There's no bending that occurs on this shaft because of that motion of the rotor system moving around. And so the reason that happens is because when we take this propeller, let's have a look at it. If I take this propeller like this and it's running in this direction, this way, and I want to move it, and I'm going to do this motion, I'm going to turn it just like this. If I take the propeller and I move it, or my rotor, I move it 90 degrees so I can see what's happening in this axis right here, just like this. When I tilt this rotor system or this propeller like this, you notice what happens is as it tilts, the angle of attack of this blade right here decreases. On the other side, what happens is the angle of attack of this blade increases. What that means is that the lift on this side of the blade increases and the lift on this side of the blade decreases. That moment that's generated because the aerodynamic forces of this propeller cause this propeller to want to move in this plane, but because it's spinning, it moves 90 degrees. And so the force, so the resultant rate of change, the resultant in change in angular momentum occurs 90 degrees, and so it moves in a direction that I'm causing my hub to move. So, what that means is that while the helicopter has this angled delta 3 hinge, right, that means that this blade really is locked solid in the plane of rotation, right, because when it moves, it changes the angle of attack. What that means is that we don't necessarily have to have a perfect delta 3 hinge. The angle can be anywhere from, like you see here on this flapping hinge, it can be anywhere from that to about 45 degrees. 45 degrees, I haven't done the math, but I think 45 degrees is the angle of diminishing returns. Okay, so you can see what happens in this flapping blade right here. I'm like this, and so this blade is allowed to flap, and what that means is it's going to be sitting here and it's going to fly at an angle. It's going to fly at an angle. We call this coning. This right here, this is coning, like that. That's coning. This is coning. So it's going to cone like this, and so this rotor blade, this propeller blade, is going to fly in a plane, and the angle that this blade makes, like this. This angle right here, is going to be essentially how far it's out of plane like this is the sign, is the thrust that's on this propeller. You know, the average thrust. It's going to be the thrust level from this one blade, the lift, and then the this part is going to be the tension, the centrifugal force holding this blade down. You can actually look at a helicopter, right, like this, and you can look at the coning angle, and you can calculate how much the helicopter weighs by knowing what that angle is, or you can calculate how much tension is in this blade by knowing what that angle is and how heavy that machine is, and so forth. So what happens is the blade is flying like this. When I pitch this in this direction, it increases the angle of attack of the blade here, which then precesses 90 degrees like this. So what that means is, as fast as I can move the aircraft like this, that change is going to cause this rotor system, the propeller, to move and stay in direction. And because it's got this hinge, it does not transmit any bending through here. Now, it's not perfect, because what happens is there's a moment that's generated in this system, and that moment is the thrust on this hinge from this blade, because for every action there has to be an equal and opposite reaction. The thrust going this direction has to be reacted by this hinge right here. And so there is a moment generated by this hinge because of the offset of the hinge pin from the rotational axis of the motor. So we do get, in this configuration, we're going to get some precession. And in this model, the model is heavy enough, and this motor has got quite a bit of its own inertia. If I were to take this propeller off, let's do this experiment. I haven't done that yet. If I were to take this propeller off, like this, electric motors are wonderful things. I can run it without a load, and it's going to be perfectly happy Dan. Plug it in. Yes, I know. I plugged one in with the propeller and all that kind of business, and I know a bunch of people are freaked, but you know, yeah, I can be a dumbass. Okay, so I can start this motor like this, and it can run, and we can repeat this test again with just the motor running, and we can get the baseline precession of the motor. Now, so this is a baseline right here. So the motor's running nice and happy down, and there's really not a whole lot of precession here when I do this. Those lead outs are like really slamming around. On a bigger motor, it might be more significant, and when I run like a 28 or a 35 millimeter motor, it definitely, the precession from the motor is definitely noticeable. Now the real question is how much impact does it have on the airplane? Is it a little? Is it a lot? You know, and that's one of those things that kind of depends on how big the propeller is. The next question is where am I going from here? The next step in this progression is that I'm going to build a 10-inch propeller to fly on the profile model, and that 10-inch propeller will work with this hub like this. This hub is plenty sturdy. The hub is designed to run 35,000 RPM with this 7-inch carbon fiber blade, which means that at the 12,000 RPMs that we run on our electric models with a blade that's slightly heavier, the hub is going to be perfectly fine for running those tests. In the future, you know, there's lots of ways we can go. You know, there's a lot of options. You can go 3 blades. You can do 2 blades. My intuition tells me that some form of hinge offset, probably like 10-ish degrees, like this, rather than this pin going in square, the pin having 10, maybe 15 degrees of offset would be good. You know, there's a lot of ways to accomplish that. We could actually even leave the hinge square, and then just take the yoke part and turn the yoke a little bit, offset and turn the yoke a little bit, so that the net result is that the propeller blade gets angled a little bit. There's a little bit of offset to that. That's probably the best solution. I don't know, but that's definitely in my plans for experiments and manufacturing to do. I don't have a CNC machine in my shop here, but I have I think I have some access where I can get that kind of thing done. I do have a CNC that's a router, but it won't do stainless steel. This part needs to be, the hub needs to be made out of stainless steel. It's the only thing to do that particular job with. And so the propeller blades, I don't know if I have just a propeller blade available that we can look at real quickly. But the propeller blades have a insert in them to yeah, these are half A ones here. I've done quite a bit of propeller work on the free flight models and speed models. I haven't. There's no parts there. Here are hubs, and this is the spindle that goes inside of the propeller mold. So there's a lot of very interesting information here. You know, like some questions might be, how well does it go on an airplane, and where, you know, it always flops around like that, and you know, isn't that a problem? Yeah, it is kind of. But if you look at how the propeller interfaces with a spinner, you know, the spinner will keep the propeller blades from going back very far, and so they'll keep the propeller in a fairly decent motion for takeoff and landing kind of thing, and spin up. Starting the F1C models, what we do is we just tilt the nose down and get the propeller blades looking like this when we stuff the nose into the starter to get the motor started. That's probably not desirable for something like a stunt model, but certainly this just this modification of doing the propeller, just this, going to a propeller made like this for a control line model will be a very significant advancement in terms of reducing the impacts of centrifugal acceleration and precession.